This is the 2017 WACE Specialist exam. Let's start with the non-calc section. Okay, the question 1 says let z equal a minus bi, where a and b are both greater than 0, and we consider w, and we're trying to find the possible values for the argument of w. So first, let's just write out w, which is z, which is a minus bi, plus I times the conjugate of z. Remember that conjugate of z, you need to split the imaginary part, so the conjugate of z will be a plus bi. Now let's just expand and simplify this. And remember that I squared is -1, so this just becomes negative b. And we'll factor out an I and in the ai minus bi there. So now that's w, and we're trying to find the argument of w, which is the angle that w makes with the x-axis. So the positive x-axis. So if this is w, for example, we're trying to find this angle. And if w is like here, we're going to find this angle. Now to get this, well, first there's actually two cases where you have to consider. First, what if a is greater than b? That means that a and b are both going to, the real and the imaginary part are both going to be positive because a and b are both greater than 0. So you'll have w in this quadrant, first quadrant. And that's the angle we're trying to find. Label that theta. And the thing is, it goes a minus b across and a minus b up. So obviously, if you do a little bit of trig, and tan theta equals a take b over a take b, well, this is just 1, which means you get theta equals pi over 4. So that's one case. Now the other case is what if a is less than b? So let me just draw this up. Now a is less than b. Now again, because a and b are both greater than 0, if a is less than b, then the real and the imaginary components are both going to be negative. So this will be the other case, where w is in the third quadrant. And this is the angle theta that we're trying to find. Again, same thing. It goes a minus b across and a minus b down. So theta would be pi over 4. But since we're trying to find this angle right here, it will be the argument of w will be -3 pi on 4, because this time we're going clockwise. So the answer to our argument of w equals -3 pi on 4 and pi on 4. Now question 2 gives us a cubic, where it says that z is a complex number, so it's got complex solutions. And part A says show that z minus root 2y is a factor of f of z. So that means if z minus root 2y is a factor, then f of root 2i would have to equal 0, right? Because that's the factor theorem. So let's just sub in root 2i. Remember, to get this, you just go z take root 2i equals 0, and from there you get z equals root 2i. So f of root 2i is 2 times root 2i cubed, take 5 root 2i squared, plus 4 times root 2i, take 10. And when we simplify this, you get 2 times 2 root 2i cubed, take 5 times 2i squared, plus 4 root 2i, take 10. Now this is 4 root 2 I cubed. Now since I cubed equals negative I, this is just going to become I, and there will be a negative at the front. And then this will be take, and this is take 10I squared, but since I squared is negative 1, it just becomes plus 10. And then plus 4 root 2I, take 10. And this and this cancel, and this and this cancel. We get f of root 2I equals 0. Therefore, z take root 2I is a factor. Part B says that given z minus root 2I is a factor, state another factor. So to get the other factor, you just get the conjugate of this. So that means that z plus root 2I is a factor. And that's from the complex conjugate theorem. Now part C just asks us to solve the equation, solve this cubic equation. And you'll notice that that's the same as f of z. We're really just solving f of z equals 0. So obviously we've got 2z cubed, or f of z is this, 2z cubed take 5z squared plus 4z take 10. And we know two factors, so we can almost factorize this fully. Z plus root 2I and z take root 2I. Now because it's a cubic, it's going to multiply by a linear factor, az plus b. And from here, we've got z times az. Actually, let's just simplify this a little bit more. So these brackets have just simplified to this. And now we've got z squared times az. And that should give us 2z cubed. So z squared times az, sorry, that should be 2, equals 2z cubed, which means that we get a equals 2. So we'll put that in instead of a. And now, to get b, well, this 2 is going to multiply by the b to get negative 10. So if 2b equals negative 10, then we get b equals negative 5. And we will put that in. Instead of b, we put negative 5. And now to solve f of z equals 0, we just set this equal to 0, right? So z squared plus 2 times 2z take 5 equals 0. Using the null factor law, we get z equals plus minus root 2I. And from here, z equals 5 over 2. Now question 3 gives us this integral, and we're meant to use a substitution x equals tan u to show that this integral equals this, and we go to set bounds. Well, first up, if x equals tan u, then u equals inverse tan of x. And from there, we can get the lower and upper bounds. Remember that this is x equals 0, and this is x equals 1. So I'll put this here, x equals 0 and x equals 1. And we've got to convert them to u bounds because we're using this substitution. So the lower bound, which is a, that's going to be inverse tan of 0 because that's the lower bound there. And that's 0. And now b is the upper bound here. And that's going to be inverse tan of 1 because that's the upper bound there. That's going to be pi on 4. There's a and b. And now we need to substitute everything. So if x equals tan of u, then dx du equals secant squared u. And from there we get dx equals secant squared u du. And now we can substitute everything. So we've got the integral from 0 to pi over 4 of, well, x squared, so that's tan u squared over 1 plus x squared. So 1 plus tan squared u, and then that squared. And dx is just secant squared u du. So we've subbed everything in, and now we've just got to simplify to try and get to this. So we've got this from 0 to pi over 4. Tan squared u, secant squared u, over. Now, this thing right here, 1 plus tan squared u, that equals secant squared u. And since that's being squared because of this, that's going to equal secant to the power of 4u. And that's what we're going to put in here. And simplifying this more, we got the integral from 0 to pi over 4. This secant squared you can just cancel with this, and this becomes a 2. So we've got tan squared u over secant squared u du. Now, if we convert this tan squared u, if we convert that to sine squared u over cos squared u, and this secant squared u, we just turn that into 1 over cos squared u, you'll notice that this 1 over cos squared u cancels out with this cos squared u. So we've actually got the integral from 0 to pi over 4. Since this and this cancelled, we're just left with sine squared u du. And that is part A. Okay, now part B tells us to evaluate the integral. And, well, first off, from part A, we know that it's equal to the integral from 0 to pi over 4 of sine squared u du. Now, we don't know the integral of sine squared u exactly. So what we're going to do is we're going to use a trig identity. And we'll use the trig identity cos, actually I'll write that in different colors, sorry. Cos 2a equals 1 take 2 sine squared a. And this right here, this rearranges to sine squared a equals a half take a half cos 2a. And this bit is what we're going to put in instead of sine squared u. So this will be the integral from 0 to pi over 4 of a half take a half cosine of 2u du. And now obviously we can integrate this easily. So this will be a half u take, it should be 1/4 sine u, sine 2u, sorry. Because when we differentiate this, we should get back to this. And that's going to be from 0 to pi over 4. And we'll just sub everything in now. So we've got half times pi on 4, take 1/4 sine of 2 times pi on 4, so that's going to be pi over 2. Take a half times 0, take 1/4 sine 2 times 0, which is still 0. And all of this just becomes 0, so we can ignore it. And this will be pi over 8, take 1/4 times 1, since sine of pi on 2 is 1. So this will be our final answer. Now question 4 gives us a function, which is a square root function. And part A wants us to sketch the graph of f inverse. So remember, that's just a reflection. I'll write this. Reflection over the line y equals x. So we'll draw in y equals x, like dotted line. and we're just gonna draw the inverse. So we're just gonna reflect it over. And what's really happening here is all the x and y values, they're swapping. So x maps to y and y maps to x. That's what's really happening with the inverse function. So this right here, 4, 1, that actually becomes 1, 4 on the inverse function. And it's got an x-intercept at 5, so it's going to have a y-intercept at 5. And it goes through 8, -1, so it's going to go through 1, -1, 8. Notice how the x and y values are just swapping. And we will draw that in. Probably should have drawn this better, but you get the idea. And obviously we're going to label this, so this is y equals f inverse of x. That is part A done. Now part B wants us to get the defining rule for f inverse, and it wants the domain. Well, for f inverse, well, first we start off with y equals 1 take root x take 4. That's f of x. And to get f inverse, you just swap the x and the y. So x equals 1 take root y take 4. And we're just going to rearrange for y. So we've got root y take 4 equals 1 take x. So y equals 1 take x squared plus 4. And it wants the domain. Well, first we write f inverse of x equals 1 take x squared plus 4. And it wants the domain. So we can just look at the domain of this graph right here. That's obviously x is less than or equal to 1. It's just going left from 1. So that's x is less than or equal to 1. And that's what we're going to write here. So x is all reals and x is less than or equal to 1. Just from looking at this graph. And if you don't know the graph, then what you can do is, if you have f of x, its range, so the range of f of x becomes the domain of f inverse of x. And the domain of f of x becomes the range of f inverse of x. So domains and ranges are swap. So you can see here that this is f of x, so this is y equals f of x, and its range is its range is y is less than or equal to 1. So the domain of f inverse is just going to be the range of f of x, so it's going to be x is less than or equal to 1. And that is how you do B. Part C gives us a new function g, and it wants us to get the expression for f of g of x. So f of g of x, well, that's just substituting g of x into f of x. So since g of x is 1 over x squared, so it's basically f of x, but instead of x, you write 1 over x squared. So that's going to be 1 take root 1 over x squared take 4. That will be f of g of x. Now part D wants the domain for it. Well, first of all, you can't, well, I'll just rewrite f of g of x here. You've got 1 take root 1 over x squared take 4. Well, first of all, you can't have a 0 denominator. So obviously x squared does not equal 0. So our first part will be x does not equal 0. That's simple. Now the other thing is, you can't have a negative inside the square root, because then it won't be real anymore, right? So everything inside the square root has to be greater than or equal to 0. If we solve that inequality, we've got 1 over x squared is greater than or equal to 4. X squared is less than or equal to 1/4. So we get x is between -1/2 and 1/2 from solving that inequality. So that will be our other condition. So first up, x is all reals. And first of all, x is not equal to 0. And x exists between -1/2 and half. So that will be your domain for f. Now, now question 5 is a big question, and it's worth 6 marks, and it wants us to graph this function right here. What I like to do with these is first write out the function where everything is factorized. So that's the numerator, which is already factorized. And the denominator is going to be x take 4 times x plus 2. And then I also like to write everything expanded. So the numerator is going to be x squared plus 8x plus 12. Denominator is going to be x squared take 2x take 8. Okay, now first let's find the vertical asymptotes. The vertical asymptotes is when the denominator equals 0, because you can't have a 0 denominator. And from that we get x equals 4 and x equals -2. So those are our two vertical asymptotes. And obviously we can't cancel anything out, so those have to be vertical asymptotes. And this one right here, x equals 2. Okay, now let's find the roots. The roots is when f of x equals 0. So in other words, when the numerator equals 0. And that's going to be at x equals 3 and x equals -1. So x equals 3 and x equals 1. Okay, now that we have the vertical asymptotes and the roots, let's get the horizontal asymptote now. And that's just the limit as x tends to infinity of f of x, right? Because we're looking at the behavior as x gets really, really big or really, really small. Well, in this case, it's going to be the same. And that's because, well, first, since the degree of the numerator is the same as the degree of the denominator, we can just divide the coefficients. So this equals -4. And because they're both quadratics, that's going to be the same as the limit as x tends to -infinity. Because the highest power is even. And so we've got a horizontal asymptote at y equals -4. So you can just look at it like, because the degree of the numerator and the denominator is the same, we can just divide the coefficients of the highest power, and that's just y equals -4. So we will do our horizontal asymptote right here. Okay, now we've got some weird business going on here, because this graph could look like something like this. If we just ignore all the points we know, it could look something like this, with this here and this here. Or it could be like this sort of thing, with this here and this here. So how do we know which one it is? Oh, the first hint is that we just got these 2 points, and if the graph looks like this, for example, it can't go through those points. So that's the easiest hint, so we'll just use that. And so now we know we have this quadratic looking thing in the middle, but we need to find its turning point, right? So how do we get the turning point? Well, it's really easy without differentiating, because you can use this little trick. So if you look at the numerator, the quadratic in the numerator is when you set it equal to 0, you get x equals 3 as a root and x equals -1 as a root. So that means that the numerator's turning point is at x equals 1, right? And if you do the same thing with the denominator, you get x equals 4 as a root and x equals -2. And the denominator's turning point is also at x equals 1. Now, since the numerator and the denominator have the same turning point at x equals 1, the entire function will have a turning point at x equals 1. And not only that, because the numerator and the denominator have the same turning point at x equals 1, the function is going to be symmetrical around about x equals 1. So first, let's just find the turning point at x equals 1. If we do that, we just go to sub in f of 1 to get the y value. We got -4 plus 8 plus 12 over 1, take 2, take 8, which is 16 over -9. That's -16 over 9. So we've got a turning point at 1, -16 over 9. And what that looks to be around about here. And now let's also get the y-intercept. So that's going to be when x equals 0. And that's going to be 12 over -8, which is just -3 over 2. So we're going to have a y-intercept here. This is 1, -16 over 9. And this is the y-intercept, -3 over 2. And now obviously we can just connect all of this up. And remember, it's symmetrical about x equals 1. And since it's one of these turning points functions, so there's a turning point in the center, because the numerator and the denominator are both quadratics, the rest of the function is going to be underneath the asymptote. And we have this, and it's just going to be symmetrical on the other side as well, since the entire function is symmetrical about x equals 1. And that is our final graphed function. Now question 6 gives us a circle and a ray in the complex plane. The ray has the equation argument of z equals inverse tan of 2. So this angle right here with the x-axis, that's inverse tan of 2. And the circle is this, obviously, and it wants us to get the equation for the circle. So since it's in the complex plane, we're going to have to use the complex locus equation thingy. And because, well, it's going to be z minus I, because it's moved up 1, that's z minus I. It's going to be a magnitude thingy because it's a circle. And it equals 1 because the circle has a radius of 1. Radius is 1, so it equals 1. That's part A done. Now part B says that W, well, point P is a complex number. So this is point P. And it's the complex number W equals R cis theta. It's W. And it wants us to get R and theta. Well, theta is really easy because point P is on the, it's on the line, it's on this line right here. And that angle with the x-axis is inverse tan of 2. So theta equals inverse tan of 2. That's simple. Now to get R is going to be the length of this, right? That's R. And to get that, let's just find the intersection between the line and the circle. So the line, or the circle has equation x squared plus y take 1 squared equals 1. And the line has the equation y equals 2x. And let's just find the intersection between them. So we'll sub this into this. So we get x squared plus 2x take 1 squared equals 1. And simplifying, we get 5x squared take 4x equals 0. And from there we get x equals 4/5. And if we sub this into this, we get y equals 8/5. We've solved that. So its x-coordinate is 4/5, and its y-coordinate is 8/5. And you'll notice that this is just a right-angled triangle, where this length is 4/5 and this length is 8/5. And from that, we can use Pythagoras to find out this, which is what we're looking for. So we've got r equals root 4/5 squared plus 8/5 squared. And that simplifies to root 80 over 25. So we get r equals root 80 over 5, or if you want to simplify that, 4 root 5 over 5. And obviously we have dr equals inverse tan of 2. That's part B. Okay, question 7 gives us a right rectangular prism with this base, and point O is the origin, and A, B, and C have these position vectors. So A is 4, 0, 0, B is 0, 4, 0, and C is 0, 0, C. And it says here that C is greater than 0, which is important. Now, part A, determine in terms of C. Part 1 wants the vector equation for the line containing points A and E. So this line's direction vector is just going to be vector AE, obviously. So we'll do that. And here's a little trick to get this direction vector. How much have you gone in the y direction? Well, you've gone 4 in the y direction. And then how much have you gone in the x direction? Well, you've gone -4 in the x direction. And then how much have you gone in the z direction? You've gone c in the z direction. To get from A to E, you've gone 4 in the y direction, -4 in the x direction, and c units in the z direction. And that gets you vector AE. So literally, what did you do to get from A to E? And that's the direction vector for the line. Now, the rest is simple. It's just, now we need a point on the line. So the point on the line, we can just use point A. So that's going to be 4, 0, 0. Plus, and it's going to be a scalar multiple of the direction vector. So lambda times direction vector, which is -4, 4c. That is the answer to part 1. Now part 2 wants a Cartesian equation for the plane ADEC. So that will be plane ADEC will be this plane right here. And it wants the Cartesian equation of that plane. So look, to get that, we're going to have to need its normal, right? So it's a normal vector. And to get the normal vector, we're going to have to cross product 2 vectors that lie on the plane. So let's use vector AD. We'll cross product vector AD with vector, let's use AC because they both lie on the plane. Vector AC. Well, to get vector AD, to get vector AD, well, what did you get? What did you do to get from A to D? You've gone 4 in the y direction, 0 in the x direction, and 0 in the z direction. That's vector AD. And then AC is, what did you get to get from A to C? Well, you've gone -4 in the x direction, 0 in the y direction, and then c units in the z direction. So that will give us vector AD and AC. and we just need to cross product them to get the normal vector for the plane. So let's do that. AD cross AC is 0, 4, 0 cross negative 4, 0, C. And you can use your formula sheet for this, but you should get the normal vector for C, 0, 16. Now, doing this, we've got the normal vector right here. That's the normal vector to the plane. And we need the equation of the plane in the form A r dot n plus A dot n, where A is the position vector of any point that lies on the plane. So, well, to get all of that, we got r dot 4c 0, 16, because this will give us the vector equation. And, well, we can use any point that lies on the plane here. So we use 4, 0, 0, which is the position vector for point A. And we'll just put in our normal vector. And just simplifying this bit, that gives us 16c. So we've got our vector equation as r dot 4c 0, 16 equals 16c. Now to convert this to Cartesian, this is x, this is y, and this is z. And we just need to do that. So we've got 4cx plus 0y plus 16z gives us 16c. And we will simplify this by dividing everything by 4. We've got cx plus 4z plus 4c. And that is our final answer. Okay, part B. In general, the main diagonals AE and BG are not perpendicular to each other. So they're saying that these two diagonals, AE and BG, they're not perpendicular to each other. And then it says determine the value of C so that they are perpendicular to each other. They're saying what can C be to make these diagonals perpendicular? And to do that, first let's just get the vector BG and AE. Well, to get BG, you can just use that simple trick. What did you do to get from B to G? So BG equals, you've gone 4 units in the x direction. Then you've got negative 4 units in the y direction. And then you've gone c units up. So that's vector BG. And we can do the same thing for AE. So what did you do to get from A to E? AE equals, well, you've gone 4 units in the y direction, negative 4 units in the x direction, and then c units up. So there's AE. So let's write that. AE equals negative 4, 4c, and BG equals 4, negative 4c. Now, these two need to be perpendicular, which means that their dot product needs to be 0. AE dot BG equals 0, right? So if we do that, negative 4, 4c dot 4, negative 4c equals 0. We get negative 16 take 16 plus c squared equals 0. So we get c squared equals 32 and c equals root 32, because we know that c is greater than 0. And that is our answer for part B. Now question 8 is the last question of the non-calc, and it gives us the inner surface of a drinking glass can be modeled by rotating the line segment AB about the y-axis. So they're saying that this is the line segment AB, and they rotate that about the y-axis, and it gives us this little drinking glass. You can just imagine that. The radius of the glass at the bottom is 8 centimeters. which they've given here. And at the top, it's B centimeters. They've also given here. Height of the glass is H. We're saying that this Y coordinate, that's H, which is the height of the glass. And the equation for AB is this equation. That says here, part A, write an expression in terms of a definite integral for the volume of liquid contained by the glass when it is full. So we are just going to revolve the line segment AB around the y-axis between the bounds 0 and h. That's when it's full. Now, because we're revolving around the y-axis, we need the equation to be x equals something, right? So if we just rearrange this, get y over h equals x take a over b take a. So we've got x equals a plus y times b take a over h. So that is the equation for this line. And we'll be revolving that about the y-axis from y equals 0 to y equals h. So we can just use our volumes of revolution formula here. It's going to be pi times the integral from 0 to h of a plus y times b take a over h squared y. And that is our answer for A. Okay, part B says, by using an antiderivative, obtain the simplified expression or formula in terms of A, B, and H for the volume of liquid contained by the glass when it is full. So it's, in short, it's just saying find this integral that we've created in terms of A, B, and H over H squared dy. So I know it looks complicated at first, but really, if you think about it, we're integrating with respect to y. That's the y right there. And everything else, that's all just a constant. And we haven't got a y outside of the brackets either. Like, that's just not there, right? So we can just treat everything as if it were like just a number for the y. And that means that we can do the chain rule backwards. So we can add 1 to the power, then divide by the power, and then divide by the derivative of what's inside the brackets. So if we add 1 to the power, then this becomes 3, and then we're dividing by that power. So it's going to be, it's going to be 1/3 a plus y times b take a over h cubed. And then we're going to divide by the derivative of what's inside the brackets. So if we're dividing by the derivative of what's inside the brackets, well, the derivative of the inside of the brackets, it's just the derivative of this, because this just becomes 0. And the derivative of that is going to be b take a over h. And since we're dividing by this, we're actually multiplying by h over b take a. That's the same thing. And that's going to be from 0 to h. And let's make our life easier. We'll just take the constants out. So this is going to be pi h over 3 times b take a. And same sort of thing, a plus y times b take a over h cubed, and that's from 0 to h. And now it's just algebra from here, really. So not too hard. So we'll sub in y equals h here. And then we'll sub in y equals 0 here. So I'm running out of room. And, well, this is just 0. And these h's can cancel. So we've got cubed, take away a cubed. and these can cancel. So what we're really left with is b cubed take a cubed. And let's just bring this over the top, on the top of the fraction, just because we can. And that is our final answer. The marking key says that this is all you need to simplify it to. You can simplify it further, but this is all we'll do. But here you can just use difference of keys. And that is its non-calc section of the 2017 Specialist WACE exam. Now let's move on to the calc section. So question 9 says that the time t in minutes that a particular flight arrives later than its scheduled time is uniformly distributed, so that's important, where t is between -30 and 60. The population mean time is 15, and the population variance is 675. A sample of 30 arrival times is taken, and the sample mean is calculated. Now A is trying to ask, what's the probability that t bar is between 10 and 20, corrected 2 decimal places? Now first up, we want to write the distribution down, but we'll say that t bar is normally distributed and that's because the sample size is greater than or equal to 30. And no matter what the original distribution is, as long as the sample size is greater than or equal to 30, t bar, well, the distribution of the means, will be normally distributed. Now we got to write the distribution down. So now we know it's normal, and the mean is 15. And the standard deviation of the sample means, that's given by sigma over root n. And we know that sigma is root 675. And we know that n is 30. Now all of that's going to be squared because it's the variance. And we can just simplify this to make it 675 over 30. Now we just need to find this probability that t bar is between 10 and 20. And we just use norm CDF in our calculator, and we get 0.71 to 2 decimal places. Okay, part B says that if a large number of samples, each with 30 arrival time is taken, sketch the likely distribution of the sample mean t bar below. Okay, and in the diagram we have to refer to the calculation from part A. So first of all, we know that the mean is 15, so we're going to indicate that there, the mean. And we also know that 71% of the times are going to be between 10 minutes and 20 minutes. So this is where 70% of the graph is going to lie. So let's just do that. And now we can just draw our normal distribution. It should be something like that. Okay, question 10 says to consider z equals 1 minus I, shown in the complex plane below. And part A wants us to express it in polar form. Now that's easy. We know that this side is 1 and this side is 1. So our magnitude is going to be root 2. And the angle here, that's just pi on 4. You can just do tan inverse of 1 over 1. And you should get pi over 4. And because it's clockwise, the angle is going to be negative pi on 4. So the answer to part A is root 2 cis negative pi over 4. Now part B wants us to express z squared, z cubed, and z for an exact polar form. But that's pretty simple. We can just use De Moivre's theorem here. So z squared is going to be root 2 cis negative pi over 4 squared, which is going to be 2 cis, and this, remember, just multiplies in here, so that's negative 2 pi on 4, or negative pi over 2. Now z cubed is 2 cis negative pi over 2, which is z squared, times z, which is root 2 cis negative pi over 4, which becomes 2 root 2 cis negative 3 pi over 4. And that's because these multiply and the angles inside add. And you could also use the Morris theorem on this. Now z to the 4 is just root 2 cis negative pi over 4 to the power of 4. This time I'm using the Morris theorem, and that's going to be 4 cis. Now this multiplies in here, which is negative 4 pi on 4, which is negative pi. Now that's negative pi, but remember we need to put that into the domain of theta, so that's going to be 4 cis pi. Now part C just asks us to sketch them in the Argand diagram, so let's do that. So now let's just sketch them. Z squared is going to be here. Z cubed is going to be here. And z to the 4 is going to be here. Whoops. And that is our sketch. D just wants us to look at geometric transformations when we're multiplying by z. Now that's pretty simple. If we look at these, every time we're multiplying by z, it's rotating clockwise about the origin, 45 degrees, right? That's one thing. And how is it being stretched? Well, every time we multiply by z, the modulus multiplies by root 2. So it's stretched by a scale factor of root 2 every time. So that's going to be our answer. Down here, so it is rotated clockwise about origin 45 degrees and enlarged by scale factor of root 2. Now question 11 gives us a graph in a slope field, and it says that a series of magnets is placed under a glass plane and some iron filings are sprinkled onto the glass. The orientation or slope of the iron filings, as determined by the magnetic field, is shown below. One of the lines of magnetic force that passes through the point A, 0, 1 is also shown. So that's this right here. And now part A says, well, the slope field is given by dy dx equals that, and x can't equal 1. Now part A says, determine the value of the slope field at the point A is 0, 1. So we know that dy dx is 1 over 2x take 2. Now it's at x equals 0, so we sub in 0 for x. 2 times 0 take 2, and that's negative 1/2. So that's our answer. Now part B wants us to explain the orientation of the iron filings at x equals 1. Now at x equals 1, well, there is no slope, like it's undefined because it's kind of like infinite, right? So we just have to write that the slope is undefined at x equals 1. And like, because if you sub in x equals 1 into here, you get 1 over 0, which is undefined. So that's all you have to write. Okay, part C just wants us to get the equation of this graph right here, right? The line of force. Now, we're given that dy dx equals 1 over 2x take 2. What I'm going to do is I'm going to factor out a half here. So we've got a half times x take 1. So now when we integrate, we get the antiderivative, we get y equals a half ln the absolute value, don't forget that, of this plus c. And now we're given this point 0, 1. So let's just sub that in. And now that 0 take 1, this just becomes ln of absolute value of 1. Now that's 0, so this thing all just cancels out. And we get that c equals 1. So we can put c equals 1. So we're just left with y equals a half ln of x take 1 plus 1. Now just a quick note, the marking key gives an answer of y equals a half ln of 2x take 2 plus 1 take a half ln of 2. Now note that these two are the same thing, same. It's just that this is easier to read, and I can show you why they're the same. Because this is the same as a half ln of 2x take 2 take a half ln of 2 plus 1. And remember, we can divide these things now because of the log laws. So we got a half ln of 2x take 2 over 2 plus 1, which is a half ln of x take 1 plus 1. So they're really both correct. You get full marks for putting either answer. Now question 12 gives us a graph, and it gives us the equation root x plus root y equals 3. And a and b are the intercepts of this curve. A tangent is drawn to the curve at point 1, 4. So this is our tangent. Show that the equation of the tangent is 2x plus y equals 6. So for that, we can just use, well, we could use implicit differentiation. We could rearrange, it doesn't matter. I'll just use implicit differentiation. So we have root x plus root y equals 3. And now we just differentiate everything. So we've got 1 over 2 root x plus 1 over 2 root y times dy dx equals 0. And now we know that it's at 1, 4. That's what the tangent is at. So let's just sub that in. So we've got 1 over 2 root 1 plus 1 over 2 root 4 dy dx equals 0. And let's just rearrange for dy dx. So we've got 1 over 4 dy dx equals negative a half. And from there we get dy dx equals negative 2. So right now we have y equals negative 2x plus c. And now let's sub in 1, 4 into here because that's the point on the line. And we get c equals 6. So we have y equals negative 2x plus 6, or 2x plus y equals 6. Done. The shaded region on the diagram is bounded by the curve, the tangent, and the x-axis. Determine the exact area of the shaded region. So we're trying to get this area right here. And for that, well, we're going to have to integrate this curve from there to there. And then we will subtract this area right here, the area under the line. And that should get us that area, the green area. So let's do that. Remember that it's the integral from 1 up to a, which is, well, we have to figure that out. So now the equation of the curve is root x plus root y equals 3. Equation of the line is y equals negative 2x plus 6. Let's rearrange this to make it y equals 3 take root x squared. Now we need the x-intercept of the curve, so that's when y equals 0. So we've got root x plus 0 equals 3. So we get x equals 9. So we've got our point A, which is 9, 0. Now we also need the x-intercept of the line, right? To find this, so that we can subtract that area. So that's, again, when y equals 0. So we'll do 0 equals negative 2x plus 6. and we get x equals 3. So it intersects the x-axis at 3, 0. Now we just have to find the area. So the area is going to be the integral from 1 to 9 of the curve. So that's going to be 3 take root x squared. And we're going to subtract the area from 1 to 3 of the line. You can see that right here. We're doing the integral from, this is 9. We're doing the integral of 1 to 9 of the curve. And we're subtracting the integral from 1 to 3 of the line. And we get that shaded green area right there. Putting that in a class pad, we get 4 units squared, which is the correct answer. Okay, question 13 tells us a cable in the bridge is required to support a weight of 10,000 newtons. Tina tests a random sample of 100 cables, and the sample mean is 10,300 newtons, and the sample standard deviation is 400 newtons. Now part A says that based on Tina's sample, obtain a 95% confidence interval. Now for that, we know that it's going to be, well, the mean takeaway k times sigma over root n, comma, the mean plus k times sigma over root n. And to get all this, let's just write the distribution down first. We always want to do that. So x is normally distributed, and it's normal because n is greater than or equal to 30. So x is normally distributed, where the mean is 10,300, and the standard deviation, that's sigma over root n, and we know that our sigma is 400 and n is 100, so it's root 100, which is 400 over 10, which is 40. So that's going to be 40 squared. Now we have everything, and we also know that k equals 1.96 because it's this 95% confidence interval. So let's just sub everything in. Now if you do all of this, you should get 10,221.6, comma, 10,378.4 newtons. And you can just do all this in your class pad. Now part B gives us these statements, and it's asking whether they're true or false, and they want reasons. So part 1, if another sample of 100 cables is taken, then the sample mean will fall within the confidence interval found in part A. Now, this one is false, and that's because it's random sampling, you can't have certainty in there. Because we're selecting 100 cables at random, and so maybe you select 140 cables, which lowers the mean, and that's why it might not always fall within the confidence intervals. And that's why we can never be certain with random sampling. Now part 2 says, if a single cable is selected at random, then the strength of the cable will fall within the confidence interval found at part A. Now this is false again, and that's because we're selecting a single cable. So that means that there's more variation in the distribution of single cables. And because there's more variation in the distribution of single cables, we might accidentally pick something that's outside of the confidence interval because it could be a faulty cable or something like that. And we're not doing any means, so that's why it may fall outside the confidence interval. That's part 2 of B. Now for part C, John, a colleague of Tina, said that the cable strengths are not normally distributed, so the calculation for the confidence interval is incorrect. How should Tina respond? Well, first, John is incorrect. And that's because we are selecting many cables where n is greater than or equal to 30. So that's a sample size of greater than 30. And because we're selecting many cables, it does not matter what the original distribution is. The means will be normally distributed anyway. Now part D says, a different sample of 36 cables is taken, and it's found that the standard deviation is 500 newtons. So sigma is 500 newtons. A confidence interval for the population mean cable strength is determined to be between 9,900 and 10,200 newtons. And it wants us to find the confidence level to the nearest 0.1% used to calculate the interval. So we know that to get a confidence interval, we add and subtract k times sigma over root n from the mean. And our sigma is 500, n is 36, k is what we're trying to find because we want the confidence level, and we don't know mu. We don't know our mean, but we can get the mean because when we get this confidence interval, we add and subtract the same thing, right? So the mean is just going to be the midpoint of 9,900 and 10,200. So it's 9,900 plus 10,200 divide 2, and that gets us the mean of 10,050 newtons. And that's our mean. Now, when we are doing our confidence interval, it's 10,050. We can just look at the upper bound right now. 10,050 plus k times 500 over root 36 gets us 10,200, right? Solving this on our CAS, we get a k value of 1.8. Now this is just a k value. To get the confidence level, we need to find this probability right here, where z is the standard normal variable. So getting that gives us 0.9281, and we can do this on our class pad. So our confidence level is 92.8% to the nearest 0.1%. Now we're up to question 14. A small drone is launched, and after hovering in an initial position, it flies in a straight line under the control of the operator. The position of the drone from the operator is given by this vector equation right here, where t is the time in seconds it has been flying in a straight line. The top of a mobile phone tower is positioned at these coordinates right here. That's 200, 150, 30. That's the phone tower right there, relative to the operator, and the mobile phone tower is 30 meters tall. We know that from the z value right here. Now part A says, after 2 minutes of flight, how high is the drone above the ground? Well, 2 minutes means t is 120 seconds. And we just need to find r of 120. So that's going to be 100 plus 0.5 times 120, 0.6 times 120, and its height above the ground is 50, take away 0.02 times 120. Putting that into our class pad, we get 160, 72, and 47.6. But we're only looking for the height above the ground, right? So that's going to be this, the z coordinate. So it is 47.6 meters above ground. So So part B wants the expression for the position vector of the drone from the top of the mobile phone tower after t seconds. So that means that if OT is a tower and OD is the drone, the question wants TD. That's going to be the position of the drone, take away the position of the tower. So that is our drone equation, 100 plus 0.5t, 0.6t, and 50 take away 0.02t. Take away the position of the tower, which is 200, 150, 30. And that gets us 0.5t take 100, 0.6t take 150, and 20 take 0.02t. And that's our answer. Okay, part C. The operator knows that the drone will not strike the mobile phone tower. However, the operator does not know that the drone will cause interference when it's less than 50 meters from the top of the tower. Determine whether the drone will cause interference to the mobile phone tower, and if so, how long this will occur, correct to the nearest second. Okay, so to get this, first we need to find whether the drone will cause interference or not. And when will that happen? When the distance between the drone and the tower is less than 50 meters. So we have our position vector of the drone relative to the tower. And this needs to be, well, the magnitude of this needs to be less than 50. Because this is the vector of the drone from the tower, and the distance between the drone and the tower will be the magnitude of this vector, and that needs to be less than 50, right? So that should get us this. This is the magnitude, and that needs to be less than 50. Now we'll just solve on our class pads, solving on our CAS, and if we get any solutions, then it will cause interference. So let's just put this into our class pad, and we're using solve, the solve function, and we should get an answer 174.31 t to 285.71 seconds. So because there are solutions, interference will be caused. And this just means that the drone is less than 50 meters from the tower between these two times. So 174.31 seconds and 285.71 seconds. But the question is asking for how long this will occur. So to get that, we just need to subtract them. And that gets us 111.4 seconds. But it wants us to the nearest second. So interference will be caused for 111 seconds. And that is the answer. Now question 15 says, a battery-powered model race car moves around the racetrack as indicated in the diagram below. The car's initial position is point A. So this is the initial position of the car, and it moves in this way. At any time t seconds, the velocity vector of the model race car is given by this velocity vector, that's meters per second. Determine the initial velocity vector and show this on the diagram above. So the initial velocity vector is when t equals 0, and that's negative sine of 0 on 3, which is 0, and 2 cosine of 0, which is 0, 2. So it's across by 0 and up by 2. But that's the initial velocity vector. Now part B says, write an expression that would determine the change in displacement over the first 3 pi over 2 seconds. So that's going to be the displacement at 3 pi over 2, take away, well, the position at 3 pi over 2, take away the position at t equals 0. And because it's change in displacement, we can just do this. And that's just the integral from 0 to 3 pi over 2, but the velocity vector with respect to time. And remember, there's no absolute values because it's just a change in displacement. And this is our final answer because it just wants an expression. Now part C wants us to find the displacement vector r of t. We know that displacement is the integral of velocity. So that's going to be the integral of negative sine t of 3, each component, and 2 cosine of t with respect to time. And we get that as 3 cosine of t on 3 plus c, don't forget constants, and 2 sine of t plus k. Now we need to find c and k using this. And if we scroll up here, we look at this, the initial position is point A at 3, 0. So at t equals 0, we have our position as 3, 0. So subbing all of that in, 3, 0, and that's our position when t equals 0. So 3 cosine of 0, because it's 0 over 3, and 2 sine of 0, plus c plus k. And doing this, we get c equals 0, k equals 0, just solving that. So that gets us our constants. So our final position or displacement vector is just 3 cosine of t over 3 and 2 sine of t meters. Now, it can be shown that the model race car's speed is at the minimum when it reaches point B on the track, one of the sharpest points on the curve. Determine the acceleration vector when the car reaches point B, giving components correct to 0.01. So looking up here, it looks like the point B is at y equals 2. So the car is at point B at B when y equals 2, right? So that means the j component of the position vector is when it'll be at y equals 2. So 2 sine of t equals 2. Solving that, we get t equals pi over 2. So that means that at t equals pi over 2 seconds, the car will be at point B. Now we need to find the acceleration when this is. So our acceleration vector is just the derivative of the velocity vector, v prime of t, and that is the derivative of each component of our velocity vector. So that should get us negative 1/3 cosine of t over 3 as our x component, or our I hat component, and our j hat component would be negative 2 sine of t. And now we just need to find the acceleration at t equals pi over 2. So the acceleration of pi over 2 is negative 1/3 cosine of pi over 2 divided by 3, which is pi on 6. And negative 2 sine pi over 2. And doing this, we should get, because it wants the component to correct to 0.01, we want it as decimal, and we should get negative 0.29, just putting this into a class file, and negative 2 meters per second squared. Now part E says, determine the distance correct to 0.01 meters that the model race car travels in completing one lap of the track. So it's asking for how much distance it travels when it completes one lap of the track. So if we come back up here, we know that the car travels in this direction, maybe does something like this. And when it gets back to here, we want the distance it's traveled. So obviously that's when x equals 3, right? So in the position vector, it's when the x component, or the I hat component, is at 3 again. So this right here. And that's at 3. So just solving when that is at 3. Solving that, we get t equals 0, which is when it starts, and t equals 65 seconds. So that means that for one lap, it takes 65 seconds. So now we want the distance it travels completing that part of the track. So completing the track. So that's the integral from 0 to 6pi. And this time we're using the absolute value of the velocity, because it wants the distance it's traveled upon completing one lap of the track. So simplifying this, it's going to be the magnitude of the velocity, and we have to put these in as our working outs, plus 2 cosine of t squared, and that's being integrated with respect to time, and that's the distance. We can use our class pads on this. Using CAS, we get a distance of 28.16 meters. So when it completes one lap of the track, the race car has traveled 28.16 meters, and that's our answer. Okay, now question 16 tells us function f is defined by its graph shown below. That's an absolute value function, as you can see. The constants a and b are greater than 0, where b is greater than a. Okay, so we know these coordinates, 0, b, and this is above the x-axis. This is on the right of the y-axis, a, 0, and we know this coordinate, which is 2a, b. And part A wants us to find the defining rule of f of x in terms of a and b. So first of all, we know that it's moved right by a. It's obviously an absolute value function. So it's going to be something multiplied by x minus a. And it hasn't moved up or down at all. It's just like stayed on the x-axis. So there's not going to be anything here. So this is our function so far. And we need to find k in terms of a and b. Now, since it's like a V shape, it's like this. And it's not an upside down V. This isn't what it is. Since it's like a proper V, then k is going to be greater than 0. We know that much. And k is just the gradient, right? So we just need to find the gradient now. And finding this gradient, we can just use the gradient formula. So that's y2 take y1 over x2 take x1. And we know our y2 is b, our y1 is 0, using these two coordinates. And our x2 is 2a, and our x1 is a. So we've got b over a. So our final answer will be f of x equals b over a times the absolute value of x take a. Simple so far. Okay, part B says, by using the substitution u equals 2x take a, determine an expression in terms of a and b for the value of this integral. So first thing we want to do is just let u equal 2x take a. That means that du dx is 2, so dx is du over 2. Now we want to change our bounds. So our lower bound, u1, is going to be just substituting this into here. We've got 2 times a over 2. Take a, which gets a 0, so our lower bound is 0. And now for our upper bound, u2, that's 2 times a, take a, which is a. That's just substituting this upper bound into there. Now that that's done, we can rewrite the integral as the integral from 0 to a, that's our new bounds, of f of u, since u is 2x take a, times du over 2, since that's what dx is. And we're just going to take this 2 out of there and make it a, so that's a half times the integral from 0 to a of f of u du. Now, imagine just replacing these u's with x's. So it could be a half times the integral of f of x dx. That's how a u substitution works, right? So what we're really doing, since we're finding a half times the integral from 0 to a of f of u du, that's the same as, because this is f of x, right? And this is f of u with respect to u. So we can just replace all the u's with x's, and it won't change anything. So it's a half times the integral from 0 to a of f of x dx. And the integral from 0 to a of f of x dx, that's just this area right here. And obviously this is a triangle, so this is a right angle triangle. And that's what the integral is, right? Just this area. So we can use a triangle area formula, a half base times height. Our base is a, because this is our base, and our height is b, which is this height right here. So our integral right here is just a half ab, and that's going to multiply by a half. So coming back down here, we can just replace the integral with a half ab. And simplifying that, we get ab over 4 as our final answer. So that's the integral. Now, question 17 says, after t seconds, the displacement x centimeters of a small match attached to a spring oscillates about a fixed point O according to this differential equation. Now, the initial velocity is 8 centimeters per second, and the initial displacement is 0. Determine the function x of t that gives the displacement of the mass at any time t. Okay, so we're given this differential equation where x is the displacement and its double derivative is the acceleration. And you'll notice that that's in the form d squared x over dt squared equals negative k squared x. Now this, where k is pi, of course. Now this has a general solution where the displacement, or x of t, equals a sine kt take alpha, or plus alpha, where alpha is the phase shift. Now here, we can just put everything in. So we're given x of t equals a sine k is pi, so we have pi t plus alpha. Now, we know that the initial displacement is 0. So 0 equals a sine. If we sub t equals 0 into here, this thing disappears, and we just get alpha. So a sine alpha. Now, we also know that velocity, which is the derivative of the displacement, is a pi cosine of pi t plus alpha. And it says here that the initial velocity is a pi. So let's just sub that in. We put t equals 0 into here, this disappears, and we get alpha here. Now, just cancelling these pi's, we get 8 equals a cosine of alpha. Now, this is our first equation, and this is our second. And we need to solve for a and alpha. Now, what you can do here is you could do simultaneous equation on your class pad, but you need to put a domain and stuff. What I'll do is do it manually. So we'll divide the simultaneous equations. So we have a sine alpha over a cosine of alpha equals 0 over 8. Now these a's just cancel, and we get tan of alpha equals 0, which means we got alpha equals 0. Now, subbing this into equation 2, we have 8 equals a cosine of 0, so we get a equals 8. That gives us alpha and a, and now we can just write our final displacement equation from that. So we have 8 sine pi t plus alpha, but alpha is 0. So this is our final answer. Now part B says calculate the distance the mass travels during the first 5 seconds. Now for that, it's just the integral of 0 to 5. Since it wants distance, it's going to be the absolute value of the velocity function. Now our velocity function is, so it's going to be the absolute value of our velocity function, which would be 8 pi cosine of pi t with respect to time. Now we just put this into our class pad using CAS. If this is a distance traveled, we get the distance traveled as 80 centimeters. And that is our answer. Now part C says, the differential equation of this assumes that the amplitude of oscillation is a constant over time. Now assume that friction reduces the amplitude of oscillation according to this differential equation right here. Also assume that A0 equals 8 centimeters. So at t equals 0, A equals 8. Part C. Determine the function a of t that gives the amplitude of the mass. So for this, we just need to solve this differential equation right here. And you'll remember from methods that the differential equation in the form dp dt equals kp has a solution p equals ae to the kt, where a is just a constant. So here, we will be solving dA dt equals negative 0.4a. So we know that a of t equals a0, which is just a constant, e to the negative 0.4t. Now we know that at t equals 0, a equals 8. So we will sub that in. And we get that a0 equals 8. So we have our final function, a of t equals 8e to the negative 0.4t, which is the answer. Now part D. As time passes, the amplitude continues to decrease to the point where the small mass appears to stop oscillating. This occurs when the amplitude is less than 0.01 centimeters. D. Determine, correct to the nearest 0.1 seconds, how long it takes for the small mass to appear to stop oscillating. Now it stops oscillating when the amplitude is less than 0.01 centimeters. So A of t is less than 0.01, or 8e to the negative 0.4t is less than 0.01. We will use the solve function on our class pad. So solving on CAS, we get t is greater than 16.71 seconds. Now that means that the mass stops oscillating, or it appears to stop oscillating, when t is greater than 16.71 seconds. But it wants to the nearest 0.1 seconds, so we get t equals 16.8 seconds. And that is the answer. Question 18. A young child rides a merry-go-round at a carnival. The merry-go-round has a radius of 5 meters, so the radius is 5, and completes one revolution every 12 seconds. So its period is 12 seconds. We will write that as t. The parent of the young child stands and watches at point P, right here, exactly 3 meters away from point B. So this length is 3 meters. The ride begins at point B when the child is closest to the parents, and the merry-go-round rotates in an anti-clockwise direction at a constant speed. So it rotates like this, at constant speed. At any point in time, point C is the position of the child on the merry-go-round, right here. Let t equal the number of seconds the ride has been in progress, starting from point B. Let s equal pc, the distance that the child is from the parent. And theta equal the size of angle BOC in radians. So this angle right here is theta. A. Show that d theta dt equals pi on 6 radians per second. So for that, we know that the period is 12 seconds. So that's one revolution every 12 seconds. Now, the angle of the whole circle, this is 2 pi radians. So all we have to do is do 2 pi over 12, which gives us pi over 6 radians per second. That's d theta dt, or the rate of change of theta, because the whole circle is 2 pi radians, and if it takes 12 seconds to do one revolution, then we just divide those. B. Show that s squared equals 89, take 80 cos theta. So we're just finding this distance right here, and for that, we're just going to use the cosine rule. So we know that this is 5 meters, and this is also 5 meters, this length right here, and this length is 3 meters. So this is 3 meters, this is 5 meters, then this entire length is 8 meters, and this is the angle theta. So we have our two sides, and we're just trying to find this side. For that, we can use cosine rule. Simplifying this, and that gets us the answer. Part C. By differentiating s squared equals 89 take 80 cos theta implicitly with respect to time t, determine, correct to the nearest 0.01 meter per second, the rate at which the child is moving away from the parent when the ride has been in progress for 4 seconds. Now for this, we just have to use implicit differentiation with respect to t. So we're differentiating the s squared, but it's with respect to t, so we multiply by ds dt. And derivative of this is just 0, and we've got to differentiate this. We get at sine theta, and since it's with respect to t, we've got to multiply by d theta dt. Now we're just finding ds dt because we're finding the rate at which the child is moving away from the parent, and s is the distance from the child to the parent. So ds dt is the rate at which the child is moving away from the parent. So we just divide both sides by 2s. And we also know that d theta dt is pi on 6 from the previous, from part A. Now at t equals 4, we need to find what theta is to sub into here. So we know that d theta dt equals pi over 6. So theta equals pi t over 6. Now at t equals 4, theta equals 2 pi over 3. So that's what we'll substitute into here, into right here for theta.
Now we also need to find s at t equals 4. Now to find s at t equals 4, we can just use this equation. So we know that s squared equals 89 take at cosine, and at t equals 4, theta is 2 pi on 3. Now simplifying this, we get s squared equals 129. So s equals root 129. Substituting all of this into here, let's just do that. And putting this into our class pad, we get 1.60 meters per second. Now part D is the tricky part. The parent notices that the child appears to move away from the point P at varying speeds. D. Determine the value for cos theta when the rate ds dt is a maximum. So we need to find when ds dt is maximum. And for that, let's start off with ds dt equals at sine theta over 2s times pi over 6. That's from part C. Now, let's substitute. So we know that s squared equals 89 take 80 cos theta. So that means that s equals the square root of that, right? So let's substitute this into here. And simplifying this, now if this is ds dt, and we're trying to find when it's a maximum, well, it'll take too long to differentiate and set that equal to 0. But what we can do is we can graph this on our class pad. So when we graph this on our class pad, graphing on CAS, what we're going to do is we have our graph, and then on the top, we're going to go into analysis. GSolve. Max. And finding the maximum, we know that theta, well, first we know that theta is between 0 and 2 pi, and the only theta that it's the maximum at, that's between 0 and 2 pi, is at theta equals 0.895668. Now we want cos theta when this is what theta is. So let's substitute this into cosine theta. We get cos of theta equals 0.625, which is the answer. Again, this theta has to be between 0 and 2 pi. And finally, question 19. Consider the complex equation, this. Solve the above equation, giving solutions in polar form r says theta, where theta is between 0 and pi on 2. What we're going to do is we're going to rearrange this to get z to the 6 equals a half times 1 plus root 3i. Now we're going to convert this to polar form, just this inner bit. We don't need to worry about the half. So, if we draw a little sketch of it, we've got 1 across and root 3 up. This will be a right angle triangle, and we've got theta here, the angle we need, and we need this length. So its modulus is just using Pythagoras, we get 2 here, and then using trig, we get the angle as being pi over 3. So we've got z to the 6th equals cis pi on 3. Now we're going to use De Moivre's theorem, and we will raise both sides to the power of 1/6. So we'll have z here, and we'll have cis of pi on 3 to the 1/6. But since it's z to the 6th, there's going to be 6 evenly spaced solutions in the plane. Their spacing will be 2 pi over 6, which will be pi over 3 apart. So the first solution is just going to be z1 equals cis pi over 18. So that's our first solution. And then our next three solutions are just going to be this plus pi over 3 added each time. So z2 equals cis pi over 18 plus pi on 3, because there's 6 evenly spaced solutions and their spacing will be pi on 3 apart. We have cis 7 pi over 18. Now z3 is going to be cis 7 pi over 18 plus pi over 3. And if we do this, we'll get cis of 13 pi over 18, but that's not in the domain. We only want where theta is between 0 and pi on 2. So we won't worry about z3 or any of the other solutions, because z1 and z2 are the only solutions that are in the domain of theta that we want. So our answer will be this and this. Now comes the hardest question in the exam, part B. Now consider the equation 2z to the n equals 1 plus root 3i, where n is a positive integer. This is important. B. If 2z to the n equals 1 plus root 3i has roots so that there are exactly 3 roots, and only 3 that lie within the first quadrant of the complex plane, determine the possible values of n. Justify your answer. Now what this question is asking is that when we find the roots of this, so we solve for z, and there's going to be n z's of course because it's z to the n, when we find the roots, it's asking what are the values of n so that there's only 3 roots in the first quadrant of the complex plane. So 3 roots here. So to do that, first we're just going to rearrange for z to the n. So that's going to be a half of 1 plus root 3i. And converting this to polar, which we've done before, we get cis of pi over 3. Now we've got to find z's, all of our z's. So we know that they will be 2 pi on n spaced apart, because there's going to be n roots equally spaced, so there will be 2 pi on n apart. Now, when we solve for our z's, for example, our base case, for example, z0, is going to be cis of pi over 3n. Now, our next solution, is going to be cis of pi over 3n, but we're going to add 2 pi on n in the angle, because that's the next root that we want, right? So, for example, if this is z0, z1 could be this, and we're just going to add 2 pi on n to the angle. Now, continuing this, z2 could be cis of pi on 3n plus 2 pi on n, which is this root. So this is z1. So z2 is just going to be 2 pi on n again. So we're just going to add 2 pi on n. And so on. So what we're going to do is we're going to generalize this. So we can sort of see a pattern. So what we're going to do is we're going to call k as like zk as like the kth root of z. So if k equals 0, then it's the 0th root. If k is 1, then it's the first root, and so on. And we'll remember that k equals 0 is z0, so that's the first root. And we want z0 up to z2 all being in the first quadrant. So that's going to be cis of pi over 3n, but we add 2 pi over n k times. So if k is 0, then it's just pi on 3n, which is here. If k is 1, then it's pi on 3n plus 2 pi over n. If k is 2, then it's pi on 3n plus 2 pi over n plus another 2 pi over n. So this makes sense. I'm just going to bring that k up here. 2 pi k over n. Now from here, we want all of the 3 roots, so z0, z1, and z2, they all need to lie in the first quadrant. So now if we just look at z0, for example, well, we know that n is a positive integer. So whatever value we sub in for n, it's always going to lie in the first quadrant. Because n can't be between 0 and 1 because it's a positive integer. And n can't be 0 because it's positive. So n has to be 1, 2, 3, and so on. Right? If n is 1, then we've got this angle of pi on 3, which is still in the first quadrant. Now, as you increase n, the angle here is going to get smaller and smaller. So we know that z0 will always be in the first quadrant. What we need to worry about is z2. This root right here. So we want z2 to be in the first quadrant, which means that this angle with the x-axis, it needs to be less than pi on 2. So z2 is when k equals 2. And its angle needs to be less than pi over 2 because it's in the first quadrant. So we've got pi over 3n plus, and we've got k equals 2 here, so we've got 4 pi over n, and that needs to be less than pi over 2. Now, if we do this, we're just going to solve this inequality. You can just put this into your class pad. You get n is less than 0, which we reject because n has to be greater than 0, and you get n is greater than 8.67. Now, since n is a positive integer, we've got n is greater than or equal to 9. That's our first thing. But we need exactly 3 roots to be in the first quadrant. So our 4th root, z4, has to be outside of, our 4th root, z3, has to be outside of the first quadrant. Now that's when k equals 3. So if we sub in k equals 3 into here, that angle needs to be greater than pi on 2. So we're just going to do that. Subbing k equals 3 into here, we get 6 pi over n. And that has to be greater than pi over 2. Now solving this on our class pad, we get n is between 0 and 12.67. So we obviously know that n is greater than 0, so we can just ignore this. And we know that n is less than 12.67, but since n is an integer, that means that n is less than or equal to 12. So we've got this. We've got n is greater than 9, and n is less than or equal to 12. So greater than or equal to 9, or less than or equal to 12. So if we just put these together, we get this. But since n has to be an integer, n can only be 9, 10, or 11, or 12. So n equals 9, 10, 11, or 12. And that is the answer. That was a very confusing question, but it's simple when you think through it. And that is the end of the calculator assumed section of the 2017 WACE Specialist exam and the whole exam. Thank you.